Here's another proof example in section 5.4 day 1. We are going to prove this statement up here. This is an identity. We know it's true, but we're going to try to prove that it is true. And like usual, we need to find, first of all, a place to start. We're either going to start with the left or the right. We're not going to work with both at the same time, as has been mentioned with proofs here, the style that we use with proofs. So because of the formulas that we have down here, I'm going to say that we start with the sine of 3x. Now, in the past, I have maybe said other things, that maybe we start with the most complicated side first. But in this case, we have some formulas that are very well situated to deal with this kind of problem, this 3x in here. Now, I want you to realize that this 3x, when you see that 3x on there, it's not just the same thing as saying 3 times the sine of x. That 3 cannot be put to the outside. That's on the x, and it's kind of trapped in there. So we have to figure out a way to free that up, and that's what we'll do within this process. Now, this is 3x, so it's like a triple angle. We have double angle formulas. We have sum and difference formulas, but we don't have any triple angle formulas, so we need to somehow take care of that. Here's how we're going to do that. We'll start with saying that this is the same thing as sine of 2x plus x. Now, if we say 2x plus x, that does mean here that we're going to have, we are going to have a sum formula to take a look at. So we're going to see that there's sine of 2x, there's sine of x. So there's going to be some sort of a use of this sum and difference formula. So we've got sine of, we'll call this maybe u, and we'll call this v to set it up within our formula. It looks like we'll be using this formula right here from the sum and differences. So when we do that, we will have the sine of, oops, wrong pen. We're going to have, looks like the sine of u, so that's going to be sine 2x, cosine v, so that's cosine of just plain x. And then we're going to add to that the cosine of u, as you see right there, cosine of 2x, and then sine of x. Here's something to notice about this one. We've got everything kind of almost fleshed out, except for the fact that this is sine 2x and this is cosine 2x. We don't see any 2x's in the stuff that goes on up here. We eventually want to get to that, but we can't if we still have 2x's in there. So what I would suggest is that we deal with something, or we replace these with ones that will get us to just a single value. That's where the double angle formulas come in. Now, with sine of 2x, there's really only one option, and so we'll use that here. We'll replace the sine 2x with 2 sine x cosine x, and that is according to this double angle formula right up there. Don't forget to have that cosine there with it. That still has to be in there. And then with this cosine 2x, this one's a little tricky because if you'll notice here, the cosine of 2x, it has 3 different lines to it. And these 3 different lines represent 3 different choices that we might have for substituting here. And again, I would direct your attention to what's up in this part. You'll see that we have cosine squared right here. So what I would do with this one is I would pick the version of this cosine 2x formula that only displays cosine squared, and I see that one right there. So my just inclination on this problem is to say, all right, let's do 2 cosine squared of x minus 1, and then don't forget about the sine x that's out on the outside as well. It's still sitting there. Now, you might be wondering, what if I choose the wrong one? Well, it's not terrible if you choose the wrong one. The worst that it can do is make it take a couple more steps, because we have the Pythagorean formulas, and we can always replace this cosine squared with something from the Pythagorean identity. So it's not the end of the world, but if you take a look at what you need to come out the other end, generally you can make an informed guess as to what will be the most efficient one. But anyway, now that we have that, I want to go a little bit further in terms of simplifying this stuff. Now, since this is all multiplication, we don't distribute it, we just do these two multiplied together. So that first piece is going to be 2 sine x, and then we're going to have cosine squared x in that part. For over here, we actually do have to distribute this sign, because you'll notice that there's a subtraction in the middle there. That means that we'll have, so if we do 2 cosine squared times sine, well, actually that's all the same stuff as this one, so it's going to be plus 2. We're going to just write it in the same order so that's easier to work with later on. So it's just another one of those. And then finally, the last thing is to have here, we have minus just plain sine. Okay, so now we've got it all written out. This is as big as it's going to get. It's not going to get any bigger, which is good news. But notice that we can here combine these two. These are like terms. We can combine those to 4 sine cosine squared. It's kind of like saying 2x plus 2x equals 4x. And then we can subtract the sine. Well, we're almost there. You'll notice that in this right-hand side, we have cosine squared. We actually have 4 cosine squared, and we've got, sine in there. So we're kind of close, but we just have to do one more algebraic maneuver, and that is to do a little bit of factoring. Notice that both of them have sine x, so we could factor that out, put that in front, and have sine x times 4 cosine squared minus 1. And that's really what we're looking for. That is now the right-hand side. And so that tells us that we are finished with this problem. These first few steps are the most important. These are the trickiest ones. But then after you get everything all expanded out, you can simplify and hopefully get down to the side that you were trying to prove.